The scope of the presentation is to provide an overview of the legislative and functional performance requirements for the provision of cavity barriers in ventilated facades and guidance for system selection. The approach will be to do this by a quick recap of the features of Rainscreen, a review of the CWCT performance standards, how that relates to building regulations in terms of functional requirements, our particular journey to compliance, an approach to the design of cavity barriers, their testing, key detailing, and installation. To start, and with every respect to the field expertise in the audience, something of a simplified overview of the primary features of Rainscreens. They've been developed to suit the changing demands of buildings, providing economic solutions to facade design, maintaining an aesthetic quality, and offering a technical benefit. A Rainscreen is an overcladding system utilised for refurbishment and new construction alike. As a technology, it has certainly evolved from the early systems used to upgrade the appearance and environmental performance of 1960s type concrete tower blocks. New materials and new methods of manufacturing combine to provide new scope for both creativity and performance. Today, we consider Rainscreens to be truly mainstream. We are all familiar with the Rainscreen principle being used in projects all over the UK in all sectors. Modern hospitals with clinical crisp finishes, storage and utilitarian with a designer edge and upmarket forms. Exemplar designs are commonplace and contributing significantly to a changing skyline. Large corporate development, residential, institutional and commercial schemes, including large retail developments using Rainscreens to provide a face with personality. Highbrow and high rise. Today's Rainscreen systems have matured with a pedigree and sophistication. However, it's fair to say that the market is less aware or more uncertain of the role that cavity barriers play in Rainscreen design. The objective today is to hopefully make some of that clearer. There's a huge choice in the type of Rainscreen system available. Generic types include hook-on panels, non-sequentially installed independent panels, sequentially installed panels, positively fixed cassettes, and fast-track composite backwall systems that are prevalent in the retail sector. Thank you to Euroclad and Eurobond for the above examples, and apologies to all those that I have not included, and there are many. To say the least, Rainscreens today offer variety. Variety in terms of the covering materials available, the substructures, the panel types, their size and their shape. Importantly, from the point of view of the fire compartmentation, they offer variety in terms of joint type. Typical generic types being open joints, labyrinth joints and baffle joints. These are important as each has an associated cavity size which is required in order for the Rainscreen to function. In terms of how Rainscreens function, we can say that they are non-structural elements used as a primary weatherproofing. They're designed to circulate air through the system, expelling moisture. At the same time, the facade must resist wind forces, seismic forces and dead load. They differ from sealed facades in that they utilise the effects of air movement within the cavity. The principle is to allow ingress of air at the base and egress of air at the top. The majority of water is deflected off the face of the facade, with any penetrating water being disposed of through drainage. Perhaps there are two primary systems, drained and ventilated or pressure equalised, where pressure inside the cavity is equal to pressure outside, and there is therefore no impetus for moisture to be driven into the structure. From the cavity barrier manufacturer's point of view, or more precisely in very simple terms, the basic definition of a Rainscreen can be considered as a facade assembly comprising an outer panel, a ventilated cavity and an inner leaf. How do we bridge the basic needs of Rainscreens with the need to provide cavity barriers in Rainscreen walls? These functional requirements present a paradox. The requirement to maintain ventilation and drainage is at odds with the need to fully seal the cavity to prevent the spread of smoke and fire. this presents a conflict. How do we overcome this conflict and do so in practical and safe terms? This is not a new question. As a responsible company, we began asking ourselves how to best achieve a solution to this problem over 20 years ago. The big question is, how do we comply and be seen to be compliant with both requirements? The journey to compliance has not been quick or straightforward. In the 1980s, there was little or no guidance available for the specifier, contractor or manufacturer to determine appropriate compartmentation measures within rain screens. In the early 90s, with the infamous Knowsley Heights fire, there began a focus to research into the risks and fire performance of this new technology of external cladding. We've heard some information relating to the case detail of this fire from the previous speaker, Stephen Howard. In the later 90s, despite revisions to the building regulations, which were a consequence of that case, and the publication of research papers into fire risks and external cladding systems, we were no further forward in providing definitive solutions for compartmentation within open and ventilated facades. Cavity barrier systems remained ad hoc and included the use of standard fire stop materials that were usually installed to fully seal a cavity, but for rain screen applications were installed at a reduced width to maintain a clear, open, nominal 25mm continuous ventilation gap. The advice at the time was that this arrangement would restrict the passage of smoke and hot gases as much as practical. With the maturing market and an ongoing sense of dissatisfaction with ad hoc and assessed products, we began the development and testing of dedicated intumescent-based products. Our motivation was to provide a hybrid material that would maintain the desired ventilation cavity, allowing the rain screen to function, until such time, or rather such temperature, that the intumescent material at the outer edge of the barrier would expand to seal the void in the event of a fire. In the absence of a clear legislative framework, this approach was accepted by our customers as best market practice and inherently fire-safe by design. In parallel with the emerging market for curtain walling and external cladding systems, the CWCT published standards began to provide a reference point for compliant cavity barrier provisions. These were most recently addressed in the 2006 publication of the standard for systemized building envelopes, and the requirements were made further explicit in their technical note 73. As many or most of you will know, the CWCT standard provides a framework for specifying building envelopes. Of note, National Building Specification and National House Building Council guidelines are based on the parent CWCT standard. If we examine what the standard says in terms of air, water and wind resistance, we can see that there are different joint and cavity combinations for rain screens. The standard further states that the area of the path shall not be reduced by more than 50% at fire barriers or support rails. Applying this, we can see that the reduced air gap at cavity fire barriers for the various types of joint. If we note the open joint in the bottom row, we can see how the 25mm gap size became our design requirement when developing our cavity barriers. All of our rain screen cavity barriers are developed to function within this required 25mm minimum gap. Because this is a minimum, and to account for site tolerances, the products are tested for 40mm residual air gaps. This is a key slide. It confirms that the residual air gap at cavity barriers is 13 to 25mm according to the joint type. The standard is further explicit when it states that these dimensions ensure no blocking of the cavity occurs. It's now accepted by the market and acknowledged by the CWCT standard that the conflict between the needs for ventilation and fire sealing can be overcome by the use of intumescent materials which allow the cavity to be maintained under normal circumstances but seal the cavity in the event of a fire. The premise of their design is that the barriers are sized and installed to maintain the desired ventilation gap, typically 25 millimetres. In the event of a fire, the intumescent will activate at a critical temperature, typically around 150 degrees Celsius, and will begin to expand. For an initial period, smoke will bypass the cavity barrier until the intumescent seal is fully closed. The integrity criterion is re-established after the initial closure. The expansion continues to fully close the void. When we look at the standard in terms of fire performance, as shown in Andy's presentation earlier, the main requirement for curtain walls that are not required to provide fire resistance is the provision of fire stopping between the external wall and compartment floors and walls. Rainscreen walls are additionally required to limit the spread of fire in the rainscreen cavity, and reference in the standard is given to building regulations for the requirements. Regarding cavities in rainscreen walls, it states that barriers should be provided to close the edges of cavities, to restrict entry of fire into cavities and to restrict movement of fire from the cavity to other parts of the building. They should also be provided to close the cavity around penetrations through the rainscreens, such as windows and doors. They shall be provided on the line of any compartment wall or floor. Cavities are should be normally subdivided with horizontal and vertical barriers at centres not exceeding 20 metres, where the material within the cavity is either Class 0 or Class 1, according to national standards, or Class C S3D2 in accordance with the European classes. Where other materials are present in the cavity, the spacing of the barriers is reduced to 10 metres. There is a further requirement, which is a short statement, but was the challenge, that the cavity barriers must be provided so as not to prevent ventilation during normal use. As stated, the CWCT standard refers us to building regs for the provisions of cavity barriers. In England and Wales, we are familiar with approved document B, which gives us guidance on ways to satisfy building regulations and relevant performance requirements. Specific guidance is given in Scotland and Northern Ireland. What do we mean by cavity barriers in terms of functional performance? The standard definition is of a construction which closes a concealed space against the penetration of spread of smoke or flame. The building regs state specific performance requirements in terms of insulation and integrity. In England and Wales and Northern Ireland, a cavity barrier is required to provide 30 minutes integrity and 15 minutes insulation. In Scotland, currently there is no requirement for insulation. In terms of testing, cavity barriers may be tested following the principles of BS 47620 or BSEN 1366 Part 1. As Stephen Howard mentioned, as an alternative approach for rainscreen walls, approved document B allows fire testing in accordance with BS 8414, where the whole system is tested. The Lamatherm horizontal rainscreen cavity barriers are tested to BS 47620. Our vertical full cavity width barriers are additionally tested to BSEN 1366 Part 1. Over recent years, we've come close to undertaking 8414 tests, but on each occasion, our cladding partner has ultimately declined the test, typically being deferred due to budget constraints. We are keen to test to this standard and would welcome any approach from any interested cladding party. Since the early 2000s, we've tested a variety of product combinations to determine the optimum intumescent specification. The specification continues to improve with advances in material technology. The BS 47620 barrier tests were conducted with the barrier fixed in a cavity between walls of a fire-resisting construction. The regime involves the standard time temperature curve at standard pressure, but the barrier is installed to maintain a 25 or 40 millimetre gap. It's acknowledged that performance within Rainscreen panels may be different, but this remains a legitimate test. Under test, the intumescent reacts to increasing temperature. The activation time and corresponding ability for the intumescent to close the cavity as quickly as possible are key criteria. For standard proprietary intumescents, when the temperature does rise, there may be a significant time delay before they expand to adequately form a seal. Regarding the evolution of our barriers, we've worked with a lot of people for a long time to ensure that the materials used in our products function immediately, when required, as required. The message is not all intumescents are the same. They typically react in different ways at different temperatures and pressures. Activation time and expansion properties are critical to the performance of the seal. It's the time to close property that's considered paramount. A time delay may not be significant in a test where the cavity is empty, but may certainly be significant in practice if there is combustible insulation or other material in the cavity, which could be ignited in the time taken to form the seal. Faster is better. For reference purposes, when tested, the Lamitherm system fully closes the cavity within 2 minutes. This refers to full depth, full width closure within 2 minutes. The initial activation and expansion reinstates the integrity criterion at approximately 20 seconds. To advance the fire safety measures for rain screens, the Association for Specialist Fire Protection is currently investigating the development of guidance material for test regime and performance criteria to be used to enable third-party approval of rain screen cavity barriers. This will specifically address the issue of seal closure time. It's expected that the guidance material will be ratified and available early 2013. At that time, it will then be possible to class the relative performance of barriers against the agreed standard. Consequently, at that time, we shall seek to obtain third-party accreditation of our rain screen cavity barriers, just as we have in place for our curtain wall fire stop systems. Third-party accredited product conformity certification schemes are encouraged by the building regulations as demonstration of compliance. When possible, specifiers should only use cavity barrier products that satisfy the published requirements and demand appropriate evidence. From Dr. Ledbetter's paper, we know that currently CE marking can only apply to the external rain screen facade. This does not include back wall constructions, related ancillaries, or the cavity barrier. For clarity, today it's not possible to provide CE-marked cavity barriers for rain screen applications. There is a CEN standard for open state cavity barriers under discussion, but there is no timeline agreed and publication does not seem imminent. Perhaps in the absence of this, we welcome the ASFP developments all the more. Third-party accreditation is better. In terms of our own product development, we can proudly say that we at Siderise pioneered this concept. We were the first to engage test houses in the discussion about ad hoc test regimes for this application. We were the first to test and we were the first to market. Today we have a range of products specifically to suit this application. They are matched to suit the rating required and whether they are installed horizontally or vertically, and they can be used in virtually any normal cavity size. Options are available to suit any required combination of insulation and integrity, performance in accordance with the regulations and standards. Importantly, they've been tested to provide the fastest activation time and closure times available on the market today. In form, they are essentially engineered strips of non-combustible stone wool, faced on top and bottom surfaces with an impervious aluminium foil. Integral high-performance intumescent material is applied to the external leading edge. The system's encapsulated in a weatherproof film which is colour-coded for identification. Green happens to be for horizontal. Simple in concept, because simple is better. From a design perspective, as the name suggests, the cavity behind a rain screen is deemed a moist zone. The barriers need to be inert, unaffected by moisture, durable and age-tested. The material selected must not corrode or otherwise deteriorate so as to affect the performance of the fire barrier during the design life of the facade. Some intumescents may be adversely affected in this situation. Vertical barriers are sized to suit the actual measured cavity and installed at the full cavity width. They're installed under compression to form a tight seal and maintain pressurization within the rain screen cavity. In terms of detailing, we strive for simplicity and practicality. We need to ensure that the tested performance stands every chance of being transferable to site. Taking a brief look at a selection of some standard details. As a head closer, we have a horizontal barrier installed, leaving the nominal air gap, enabling the rain screen to ventilate. Here we see the relationship with a vertical barrier behind, installed fully across the cavity width as required for compartmentation. At a sill detail, where the top of the cavity is sealed by a sill pressing, it's common for a horizontal full width barrier to be installed. An EPDM might be required but omitted here. Alternatively, perhaps a better solution in this location is to use again a horizontal barrier with an air gap, which is ventilated to allow for potential drainage. This may be considered a safe option in case there's a breakdown of any seals on the sill. In that event, water would have to go somewhere, and if we have a full width seal underneath, where would the water go? At jambs, the detail here requires a full width vertical barrier. This time, hopefully, you can see the relationship with the horizontal barrier and the residual air gap. At internal corners, the barriers are simply mitre joint and foil taped. It's a clearer illustration where you can see that the horizontal barrier is effectively set back from the full width vertical barrier. It's a similar treatment at the external corner condition. Vertical barriers are installed first at full cavity, horizontal barriers installed within them and the joint between them tightly abutted, joints foil taped. Here's the intersection. In terms of an installation sequence, I've provided an account in the delicate paper. In essence, the usual sequence on site is to first fix the primary brackets for the vertical frame, then mark out the positions of the vertical and horizontal barriers, install the full width vertical barrier, then the horizontal barrier, install the vertical framing element, making sure that the intumescent material is carefully cut to receive the depth of the framing section, and then install the facade panels. Simple concept, effective performance. The concept has been verified by research at BRE using the large-scale tests on rain screen walls, as per the last speaker. Part of that research stated that cavity barriers with continuous strips of intumescent material are more effective than those with perforated plates. The research also found that to make barriers effective, it may be necessary to break the vertical cladding rails so that the cavity barrier can be continuous. The research is shown in the BR135 document as posted previously. Another key slide, it's key but simple, relating to an important detail. A break in any thermal insulation in the cavity will be required at the location of the cavity barrier. To do otherwise introduces questions of integrity performance, either due to the properties of the thermal insulation material, gaps at joints, or sometimes uneven surfaces. How do we detail for compartmentation? In terms of the overriding principles, we know that elevations need to be isolated into compartments suitable for the prevention of smoke and fire spread. These barriers must not compromise the pressure equalization airflow behind the panels. Horizontal closures are required at each floor level. Vertical barriers are required to maintain the pressurization. At junctions, corners and other abutments, the fixing centres for the vertical closures need to be reduced to take into the account of increased wind pressure. For Rainscreen walls, approved document B that states that cavity barriers are provided to close the edges of the cavity, including around window openings, at the junction of the wall with a compartment wall or floor, and to limit the maximum dimension of the cavity to 20 metres where the surfaces of the cavity are class 0 to class 1, and as before, 10 metres in other cases. This also applies to shear wall conditions where a typical spacing on a large development would be 20-metre intervals. To comply with NHBC design guides, again, horizontal cavity barriers are required at each floor level. This time, vertical barriers are required at centres not exceeding 6 metres. A vertical closer needs to be placed as close as possible to an external corner, normally within 300 mil. There's also a recommendation that vertical cavity closers should be located at centres not exceeding 1.5 metre centres within 6 metres of an internal or external corner condition. This compartmentation state is in addition to the requirements of building regs for cavity barriers. However, the same barriers may be used. As a form of key summary, I would state that the Rainscreen must limit the spread of smoke and fire in accordance with approved document B. This is achieved by the installation of cavity barriers, typically 30 minutes integrity, 15 minutes insulation. We've seen that traditional methods will stop the Rainscreen system from working. Ventilated methods using intumescing material allow for the normal operation of the system and seal the system in the event of fire. In terms of some very basic guidance, here's a possible checklist for when you are considering barriers for Rainscreens. Is the system tested? Ensure that the performance matches or exceeds the minimum. Check details of the tested arrangement. Some are ad hoc and some might be surprising. Look for third-party accreditation as a demonstration of compliance. Activation time to full seal closure is important. Quicker is better. Consider the material form and installation details. Simple concepts result in practical details. Is it a total compartmentation system? Are vertical seals available from the same supplier? I would also urge you to consider only specifying or sourcing materials from ASFP members. They understand the technical and market requirements and all have products fit for purpose. On the question of support, both technical and project, what is the extent of support available to you and your business? I'd like to briefly finish by saying that full information regarding our offer, regarding these barriers and others, are included in data sheets that you can download from the website. I would also like to offer a technical paper which is in your delegate pack, which discusses all of these items further, and would like to offer my thanks for your time and patience.